What we saw in a recent segment was that the probability histogram for the binomial distribution starts to look more and more normal as you increase the number of trials. And indeed, it's a remarkable fact in probability that many distributions approach the normal curve. And as you know from Stat 2.1x, the normal curve can be completely specified by a measure of center and a measure of spread. And so what we're going to do now is start building up towards normal approximations for probabilities involving large samples by first looking at measures of centers, now not of lists of data, but of probability distributions. And the calculations are going to be very similar to what you have known how to do for quite some time now. The first thing that we want to discuss is what variable are we talking about? And we're going to talk about random variables, variables whose values are subject to chance. These are, occur naturally, and we've been dealing with them really all through this course. Several examples: the number of heads in 10 tosses of a coin is random. The number of rolls till something happens for the first time, the waiting time is a random time. How much you make in a gambling game is random. And if you move more towards statistics, for example, you might be looking at the average income of people in a sample and wondering what that says about the average income of the people in the population from which the sample was drawn. So all of these are variables in that they can take more than one value, and they're random variables in that their value is subject to chance. Taiki gets to decide what the value is. Now, as in mathematics, you're used to having letters like little x and little y represent variables. So also in probability theory, the typical notation for a random variable is an uppercase letter towards the end of the alphabet. X is the most common, as is y, probably a close second. And in what we're going to be doing, very often you're going to have the number of spots on the first roll of the die, the number of spots on the second roll of the die, or the voting behavior of the first person sample, the voting behavior of the second person sample, and so x1, the first observation, x2, the second, and so on, is often very commonly used, and as is the sum. If x1 is the amount you make on your first bet, x2 is the amount you make on your second bet, and so on, and you're making n bets, then the total amount you make is the sum of all of your x1, x2, etc. up to xn. It's the sum of the first n net gains that you make in your bets. And so we won't use a huge amount of notation, but you will see this notation in your text and elsewhere, and it's as well to be familiar with it. Just know that S stands for sum, and the n, that is the subscript here, says you're adding n terms. So we will start with a simple random variable. As always in this class, we start with something very simple and build up. And the random variable is the number of spots on one roll of a die. And it will be a useful image to have to think of this as a single draw at random from a box of numbered tickets. So one random draw from a box with these tickets in it is probabilistically the same as rolling a die and looking at the number of spots you get. So this is a random variable, and every random variable has a probability distribution. All the possible values, 1 through 6, and the corresponding probabilities, which in this case are rather straightforward. They're all 1/6. So if you draw the histogram, it is completely flat. It is a brick that stretches over these 6 values. And so now what we're going to do is we're going to look to see what we expect x to be, and really it could be any one of the numbers because they're all equally likely. But we're going to pretend we're rolling the die over and over and over again and keeping track of our numbers, and then looking in the long run what average value we get. So the law of large numbers says what? Well, this value 1 should occur about 1/6 of the time, on about 1/6 of the rolls. this value too should occur on about 1/6 of the rolls as well. And so each of these values occurs about 1/6 of the time in the long run. And so if you compute the long run average value, here's your computation. Value 1 occurs about 1/6 of the time, value 2 occurs about 1/6 of the time, and so on. And so you add up all of those and you have 3.5, 3.5 as your long run average value that you expect to get. And we'll take a hard look at this 3.5 because I know many of you are thinking, but you can't get 3.5 spots on one roll of a die. No, you can't. And this is the same situation that you had when we started talking about averages. Just because the list has only whole numbers in it doesn't mean the average has to, and this is very much the same idea. Before we get into details of that, here's a little bit of language. This 3.5 is called the expected value of the random variable, also known as the expectation of the random variable, and denoted capital E of your variable. And the key here is the expected value doesn't actually have to be a possible value. It is by definition the long run average if you repeat the experiment over and over again and just look at the entire list of values that you've got. But this is an average, and it is just the plain old average of these numbers. Let's examine that, because we understand a lot about averages, and because of that we understand a great deal about expectation. So here's a little recap. You have one draw from 1 through 6. You have the same probability distribution that we had last time. And here's our calculation for the long run average, which, if you sort it out, is simply add up all the numbers and divide by 6, which is a simple average of this list. And so what we have observed is that if you draw once from a box of tickets, then the expected value of that single draw is what is sometimes called the average of the box. An average of the box is a lazy term for the average of the numbers on the tickets in the box. So you pull a ticket at random out of any box, the expected value of that random quantity is the average of what's inside the box. And so the expected value is in fact a simple average, and therefore it has all the properties of averages, and those you understand very well. You know, for example, that the average has the same units as the original variable. So if this happened to be money, which it isn't, it's number of spots, but it happened to be money, then this would be money as well. You know that the list can have whole numbers, but the average doesn't have to, and you must not round. You know, very importantly, that the average is the balance point of the histogram. What histogram? There aren't any data here, nobody's taken a list of numbers. What you have is the histogram of probabilities. You have bars centered at these discrete values, each of which has area 1/6. Right? So the histogram looks like a brick, and that brick balances at 3.5. This is same old from Stat 2.1x. So now that's one draw from the box. That's the smallest sample you can have. What if you had a larger sample? So I'm going to now pretend I'm going to draw 200 times at random with replacement from that box, which is equivalent to saying I'm going to roll a die 200 times. And you're thinking to yourself, yeah, I'm never going to do that. No, of course you aren't. But you might someday take a random sample of size 200 from a more complicated population. So let's work our way up to that. So what we've said is that on average you expect to get about 3.5 spots per roll. So if you roll 200 times, what do you expect to get total? What is the total number of spots that you expect to get? Well, if you expect to get 3.5 per roll and you've got 200 rolls, then surely the total that you expect is 200 times 3.5. That's 700. Let's take a look at that number. What's the smallest that total can be? The smallest that the total can be is if every one of those 200 rows gave you a single spot. Now that's not very likely. The chance is 1/6 to the power 200, which is very small. But it's there. The smallest the sum could possibly be is 200. And at the other end, the largest it could possibly be is 1200, when each of the 200 rows gives you 6 spots. So the possible values stretch from 200 to 1200, and 700 is exactly in the middle of that range, which is not surprising because you're starting with a symmetric distribution and you expect the balance point to be right in the physical center every time. So this is a natural and simple calculation. And what I'd like to do now is to rewrite this in terms of drawing at random from a box. So as we said, 200 rolls of a die is probabilistically equivalent to drawing 200 times at random with replacement from the box 1 through 6. You cannot draw 200 times without replacement from this box. You will run out of tickets after the 6th roll. So if I draw 200 times with replacement from this box, then at the end of that I have a list of 200 numbers, each of which is one of the values 1 through 6. If I add them all up, that is equivalent to getting the total number of spots. So I'm looking at what is called the sum of the draws. And so here's some notation. x1, the number of spots on the first row. The expected value of x1 is 3.5. And then you have x2, which is the number of spots on the second row, and so on, x3, x4, all the way up to x200. And then you add them all up. So the total number of spots in your 200 rows is S for sum, indexed by how many you're adding, S200. That's the number of spots on the first row, plus the number of spots on the second, etc., plus all the way up through the number of spots on the 200th row. And each of these is one roll of a die, and so each of these has expected value 3.5. And so if I want the expected value of the sum, what you think must happen naturally is indeed correct. The expected value of this sum is the sum of all of these individual expected values, and they're all 3.5, and so you have 200 of each one, and that's your 700. So this is saying very formally what we wrote down with little discussion up here. And so while we're being formal, let's write down a formula. And as always, in Stat 2x, we try to write down formulas in two languages, first in English. So you draw at random with replacement from a box of tickets. Excuse me. Then the expected value of the sum of the draws is, take the average of the box, that's what you expect to get per single draw, and multiply by the number of draws you have. If you want to use math notation, you are welcome. What you've got is a sequence of n draws which are independent, you're drawing with replacement, and identically distributed, because of course every time you're drawing from the same box, this is a famous probability abbreviation, IID, independent and identically distributed. And you're then adding them all up, so Sn is the sum of your nx's, and you're computing the expected value of the sum, and that is n times the expected value of a single one, that is the number of draws times the average of the box. You expect any single one to be the average of what you are drawing from. Well worth looking at this in an example, and I will take a multiple choice test that has 100 questions. Each question has options A, B, C, D, E, 5 possible answers, exactly one of which is correct. And the grading scheme goes like this. If you get the question right, you get 4 points. If you get it wrong, they actually dock you 1 point. You get -1 point. This is to discourage guessing. But supposing you rather perversely decided that you were going to guess every single one of these questions at random, independently of everything else. Now, of course, you wouldn't do that. You're a good student, you know answers to questions. But you know what? People who set these standardized tests, they're very well aware that you can just throw darts at their paper and get a score, because it's all multiple choice. And so they are quite interested in working out probabilities that if you sat a monkey down in front of the test and said, here, answer all these questions, insisting that the monkey answer each question, that is, pick one option for each question, so no option picked, no peanut. What is the chance that the monkey would pass the test? I mean, that's worth knowing, because you want to set your passing marks and your grading scheme accordingly. So that's what you're doing. You're testing the test, as it were. So what's the question of interest? The question of interest is, what do you expect to score? And so what we're going to do is we're going to model this by drawing tickets from a box. Now, what does the box represent? The box represents one question. What can you score, that's your variable, on one question? Well, on one question you can score either 4 or -1, with a much larger chance of scoring -1 than 4, because you only have 1/5 chance of getting the 4. And then you have 100 such, and to get your score on the test, what do you do? To get your score on any test, you add up the scores on the individual questions. And so your score on the test can be modeled by the sum of 100 draws made from this box. And let me explain what this box is. This box is what we just talked about, plus me being lazy. On a single question, you can either get +4 or -1. And really, I should have drawn the box as -1, -1, -1, -1, and 4, but I'm lazy. So I just said 4 tickets labeled -1 and 1 ticket labeled 4. So when you draw from this box, you have a 1/5 chance of getting the 4 and a 4/5 chance of getting the -1. So this represents what's happening on a single question. You do that 100 times independently and then add up, and that's a model for the score on your test. So what do you expect it to be? Well, we now have a machine. The expected value of the sum of the draws is the number of draws times the average of this box. So let's find the average of that box. There are 5 numbers in this box, 4 -1s and a 4. So what's the average? 4 -1s and the 4, add them all up, and you get 0. You can divide by 5, which is the number of tickets, and you have 0. For those of you who like to calculate your averages by weighting, there is the value -1, and the corresponding weight is 4/5. And then there's the value 4, and the corresponding weight is 1/5, and this is what you'd get if you were using that probability distribution table that we've written out. Either way, you get 0. And what does this 0 mean? That means on average per question, you expect to score 0 points. Well, if that's what you expect, then what do you expect to score on the test? 0. On average per question, 0 points, and so you have 100 questions, 0 times 100 is still 0. You expect to score 0 on this test, if you guess at random. What's the most you can score? The most you can score is if you get all 100 questions correct, and that is 400 points. And the least you can score is if you get all 100 questions wrong, and that's minus 100 points. So your possible values are from minus 100 to 400. 0 is not in the center because this box is not symmetric. We'll have a lot more to say about that once we start looking at measures of spread and shapes of distributions. For now, the distribution will balance at 0. So the expected score is a natural question to ask in a situation like this, as is, how many questions do you expect to get right? That's a different question, because this now ignores the grading scheme. It doesn't matter what they're giving you or taking away from you. If you've got a question right or wrong, it's just how many do you actually get right by guessing at random. And here it is well worth looking at how this connects to what we are doing now, because many of you will be thinking, well, I've got 100 questions. I've got a chance 1/5 of getting the question right, so I expect 1/5 of 100 to be right. I expect 20 to be right. And exactly so, you are correct. What I want to do is I want to connect it to the formalism that we are developing now, so that we can do some slightly less obvious things in just about a lecture or two. And so I want to look at a sequence of right and wrong answers and discuss counting. How many do you expect to get right in terms of what we're doing now, which is drawing tickets and adding them up, sums of random things. What do sums of random things have to do with counting? Well, so supposing this was your sequence of rights and wrongs, what we'll do is we will code them. Every correct one, we're trying to count the correct one, so we'll count these as ones and everything else as zeros. Here goes. So 1, and then zeros for all the wrong ones, and a 1 for right one, 0, etc. And the observation is, here now you have a list of numbers. Add them up. What do you get? Yep, you get 3, which is the number right. Adding zeros and ones is the same as counting. See, the sum goes up for every correct answer, and then it stays flat, and then it goes up again 1 for every correct answer, flat, etc. And so counting and adding zeros and ones are exactly the same thing. So when you're counting the number right, you are still looking at the sum of draws from a box that now has, on a single question, how many questions you can get right. Well, on a single question you can either get 1 right or 0 right. And so the chance that you get the question right is 1 out of the 5 that you have in the box, and the chance that you get it wrong is 4 out of the 5. And so we have recoded our previous box into a counting box. 1 for correct and 0 for everything else. So how many do we expect to get right? Well, it's the number of draws, that's 100, times the average of this box. And what's the average of that box? 4 zeros plus a 1 divided by 5, that's 1 divided by 5, and it's a very important observation that if you have a 0-1 box, as you do here, the average is the proportion of ones in the box. And so how many questions do you expect to get right? By formula, number of draws times the average of the box, and so number of draws times the average of the box, 20, and that was the natural calculation that you were doing. So this question also, counting the number of successes, falls into our paradigm of how we are approaching sums of draws from a box. And what I'd like to do now is we've answered 2 questions about the same situation. I'd like to make sure that the 2 answers are consistent. So this is just a recap of the situation. You've got 100 questions. Each of them is multiple choice, 5 options, 1 of which is correct. Here's the grading scheme. You get +4 if you get it right. You get -1 if you get it wrong. And you have decided you're going to answer every question by guessing at random independently of everything else. And the 2 questions we have answered are, what's the expected score on the test? We said that's 0. What's the expected number of questions right? We said that's 20. Do these 2 things hang together and make sense? Well, let's check that. If you get 20 questions right, then what are you scoring on those questions? Well, for every question right, you're getting 4 points. So for the 20 questions you get right, you expect to get 80 points. Is that your score on the test? Well, no, because they're going to be nasty to you about those questions you got wrong. And how many questions did you get wrong? If you got 20 right, then you got 100 minus 20, that's 80 wrong, and for each of those they're taking away 1 point. So for those questions you are scoring minus 80 points, and so your score on the test is 80 minus 80, and that's your 0 right there, and that checks out nicely. And just to finish up, we're going to take a look at this expected number right and connect it to something we've done recently. So I'm looking at the number right, and I have forgotten, therefore, about the grading scheme. How many points you get is not my issue. It's just the question of, do I get an answer right or not? And on the 100 questions, how many do I get right? Now, what do I have here? I have 100 independent success-failure trials, right or wrong. On each one, my chance of success is 1/5, and I am counting the number of successes. How many do I get right? Well, that has a probability distribution. How do you calculate probabilities for the number of successes in a fixed number of independent trials? That's right, you use the binomial formula. So binomial, the number of trials is 100, P is 1/5. And what we have just said is that the expected value of your variable, R20, is 100 times 1/5. That is, you take the number of trials and you multiply by the probability of success, NP. And so in general, if your random variable x has the binomial distribution with parameters n and p, then its expected value is n times p. And to translate that into English, what is a random variable with a binomial distribution? It is the number of successes in n independent success-failure trials, where p is that constant probability of success on every trial. And it can be modeled by adding up n draws at random with replacement from. Now take a hard look at this box. Ones and zeros, and now I'm not writing down the number of tickets, I'm writing down the proportion of tickets. The box has a proportion p of ones and 1 minus p of zeros, so this might be 0.5 and 0.5. Or if it were a roll of a die and success was getting the face with 6 spots, then this would be 1/6 and this would be 5/6. So we're moving from writing down exactly how many tickets there are in the box to simply writing down what proportions there are of the different kinds. If you draw from this box once, then the average is 1 times the proportion of ones plus 0 times the proportion of zeros, and that sorts itself out to p. On a single draw, you expect to get p, and that is much more easily understood as, in the long run, your expected proportion is p. And so if you are adding up n of these, then you are going to get np as your expectation. On a single draw, you expect p, and so n times that. And so if you use an example, then the expected number of heads in 100 tosses of a coin, that's binomial, n is 100, p is 1/2, and so its expected value is 50, which, yes, you knew that. You did not need a big machine and a formula and calculations with p's and so on to tell you that the expected number of heads in 100 tosses of a coin is 50. So you're asking yourself, why are we doing this? Because I already know the answer. You do indeed. But most of you have been through Stat 2.1x, and you know that every time you have a guess for something, it used to be an estimate in Stat 2.1x, now it's an expected value. Every time you have a guess, in your head you're thinking, is it a good guess? And so it should come as no surprise that very quickly we're going to be saying, okay, you expect 50, but give or take what? Yes, exactly, you're going to need standard deviations, and for that, this formalization is going to be quite important. So put up with the heavy machinery for a simple thing now, and we'll draw the benefit of it in a couple of lectures.